Welcome back, everyone, to the eCoreAcademy e-learning platform. Today, my name is AJay Raj, and I'm back with yet another surprise geometry video for you all. Our new topic of focus is on parallelograms. I'm really excited about these new sequences of videos. We're going to be transferring into more complex two-dimensional figures, and we're also going to revisit that part of geometry which many of you are very shaky with, and we're actually going to take that even to another level, another step in geometry, kind of bumping it up into that eCore enrichment level type items. This is all about enrichment products and enrichment course level material. So that's what eCoreAcademy is going to be bringing to you, especially through these next various topics. We've gone over the fundamentals. We started to look over those, kind of breeze through those a little bit, but now we're going to start to actually sit through these difficult problems, scenarios, and concepts that are basically building off of these fundamental blocks. And we're also going to have a lot of fun with it as well, bringing back these different proofs and starting to decide and develop new theories on your own as well. So you guys are going to be your own mathematicians and scientists in your own unique ways. So we have some really cool course material that I've planned out to add in between these different lessons, these different challenge problems, and these different types of problems in order to correlate it and complete this course as an enrichment course. But today we're going to be looking at parallelograms, and this is part one because parallelograms is one of the largest course sections and lessons in the entirety of the geometry course. So this is going to be a very essential product of this entire geometry course. This has to do with many of the common shapes that you already know, and this is going to be revisiting to some of those basic skills that we learned originally and tying things together. So today we're going to look at the unique properties of parallelograms and their classification amongst quadrilaterals. But wait, before we jump into the meat of today's lesson, please make sure you smash that subscribe button down below, hit that like button on this video, as well as turning on post notifications so you don't miss out on any of our latest uploads on our YouTube channel at eCoreAcademy. All right, without further ado, let's jump right into it since we've already done the due diligence that this lesson deserves. So let's get into these unique properties of parallelograms, open it up, and try and classify them amongst quadrilaterals. As we'll move into our next video, part two, we'll start moving into a bit more complex theorems have to do with the theorems of parallelograms and our T-chart, which I'll also get into today as well. So what are parallelograms? Let's look at some real-life applications before we get into the geometric definition. I want to try and give some insight on what real-life definitions would be, basically identifying what a parallelogram would be occurring in real life without all of these qualifications, these side length relationships, qualifications between angles, all that fancy-schmancy classification stuff with their quadrilaterals. Let's just take a look at it, break it down, and see what it means in real life, something that we can all relate to. So parallelograms are shapes that can be represented through other quadrilaterals, such as rectangles and squares. So parallelograms have such a wide representation and come in a large variety. Now, I'm sure many of you are already familiar with a square and a rectangle before you even came into this geometry course. They're basic figures that you learned in elementary school itself. So these rectangles and squares are actually directly correlated to parallelograms. And I'm sure many of you either knew that or didn't, but these parallelograms are very essential and important, and they're building blocks for these more complex figures, even as simple as rectangles and squares, and as complex as dodecahedrons and those three-dimensional figures that'll foundate off of these 2D figures as well. And these are some examples of distinguished parallelograms in real life. Now, that's an eraser right there. Yes, that's a parallelogram. I know it's a three-dimensional figure, but it's an extension of a parallelogram. It has literally 6 sides representing that parallelogram, just as a cube would. On each side of the surrounding sides facing, whatever's making contact with it, not making contact with the surface of the table or the air on top, those are all parallelograms, as well as those top slab right there on the top with the pink eraser logo, as well as the bottom slab that's touching the table. All of its sides are entirely parallelograms. Now, even if this were a rectangle, they would also be types of parallelograms. That's how it works. And then next off, we have another building like this. This is a parallelogram structure. Now, I know parallelograms aren't very commonly seen in buildings, not necessarily not buildings. They're not the best for foundational structure, your distinguished parallelograms. But some parallelograms that would be very common would include your rectangles and sometimes even your squares. These cubes are very, very prominent, and these rectangular prisms are also prominent and good for foundating your structures and your buildings, unlike these distinguished parallelograms. And also, one thing that I really would like to put out there is if you've ever looked at a cruise ship is basically formed in the same exact manner as a parallelogram. That helps with its aerodynamics, meaning it helps it go through the water with the least amount of energy needed. And we'll actually get into explaining how that happens and how it derives from a rectangle and a triangle itself. So that's all the exciting content we can get into later on in our new videos that we're going to be coming up, these extended problems videos. But now let's look at the basics, the fundamentals, and this is the fun and easier part of this whole little section on parallelograms. So now let's start to look at it in geometry. So what's the definition of a parallelogram in geometry? So a parallelogram's geometric definition is a quadrilateral that has two pairs of opposite parallel sides. So we see here it's a quadrilateral. So that's something that tells us it has four sides. And then, of course, it has two pairs of opposite parallel sides. Meaning that these parallel sides, meaning they have the same exact slope if they were graphed on a given XY coordinate plane. And of course, they're going to be opposing, meaning they're not going to be intersecting or consecutive. They're going to be directly opposite from each other. These figures have unique angle and side length properties that will be consistent for all quadrilaterals other than trapezoids. And there goes that same exact property that I was telling you. Parallelograms have such a wide representation, and trapezoids are not a specific type of parallelogram, but that's the only type of four-sided figure that does not go under the category of a parallelogram. And that's crazy. These are all your regular figures. That's the only regular quadrilateral that does not go under a parallelogram. And that's absolutely crazy, seeing how much of a wide representation parallelograms have. And they have such a very general definition, which gives them that wide variety. Now, I know you might be thinking, oh, well, no, parallelograms, that slanty thing that kind of looks like a triangle and a rectangle meshed together, like pieces of it. But that's a distinguished parallelogram. That's specifically a parallelogram that cannot be any other figure but a parallelogram. But if you look at cases such as a rectangle and a square, they fit the definition for a parallelogram. So they're a parallelogram, but also their own given figure, such as their own rectangle and their own type of square. So let's take a look at here, this picture right here. I love this picture here because it gives all of the different properties and all of the different markings that I originally went over in our basic geometric terms and definitions video at the very beginning of the course. So if we take a look here, we can see that we have our first property stated. It's basically a quadrilateral with four sides. So a quadrilateral is a figure with four sides, and it's a regular quadrilateral. So we see that side AD, that's one. We count 1, 2, 3, 4. So it passes that quadrilateral. So let's say quadrilateral. I'm going to underline quad, say it has four sides. And then if we look at these arrowheads, it's basically saying two arrowheads, two markings, and two markings here. Whenever you have that property, what do we know about that? Well, if you have those markings and with the given definition, we know that these sides are going to be parallel, but they're also going to be congruent. They're opposite sides. They're also going to be congruent. So let's say here, so opposite and congruent when it comes to these opposite sides. So pairs of sides. I'll write here, pairs of sides. And then we get into something a bit more complex, which we'll get into in our next video, which are the diagonals of a parallelogram. You don't necessarily need to know this, but when the diagonals intersect, they actually bisect each other, meaning that they're going to have equivalent sides. So I'm just going to say here diagonals bisect. You don't need to know that. That's not going to be something that's going to be valid for this. I'll go into depth with it in our next video, so don't worry if you're confused. So diagonals bisect. And that's basically meaning it's going to split it down the center into two equivalent halves of the same diagonal. Now let's take a look at area and perimeter, a very, very basic property of our geometric figures and 2D figures. So these are the basic formulas. I'm going to go through these fairly quickly. So we have the area of a parallelogram It's in terms of base and height, not length and width, because then again, if we take a look at rectangles and squares, their side lengths are actually their base and their height, so they can just be referred to as your length and your width. However, for a parallelogram, you don't have that luxury. You have to be given an extra altitude located on the interior, just as you would be given in an oblique triangle itself. And in the perimeter of a parallelogram, fairly simple, the sum of all sides. But then again, we know that two sides, opposite sides, are always equivalent. So you have two pairs of equivalent sides. Therefore, you can just multiply each separate side, each distinguished side by 2, and then add them together. So we have this parallelogram here with our h representing our height. B is representing side 1. Or sorry, let's say side 2. Let's keep it alphabetic, in alphabetical order. And then A is side 1. So let's practice our area formula with this. What would the area be in terms of these given variables? So we know that it's base times height. So we know that our base, in this case, it's going to be side B, because then again, your base is always going to be represented by the side that's going to be intersected by your altitude. So you can see here the altitude is intersecting it at a 90-degree angle. Therefore, the B side here is going to be your base. And then this height is basically your intersection in which a side's opposite vertex, so this opposite vertex right here, can draw a straight line downwards and intersect that given side at a 90-degree angle as shown. So that's going to be the accurate height. So all it's going to be is going to be base times height equals area. And then the perimeter of a parallelogram is going to be 2 times side 1 plus 2 times side 2. We know that this is side A, so this is also going to be equivalent to side A. So we're going to say here equal to side A and then equal to side B, since they're opposite equivalents. So merely we can just plug in these values and say that for a perimeter, it's going to be 2 times B plus 2 times A equals perimeter. All right, let's move on. Let's look at the properties of side lengths. So I'll break this up into 2 slides: the specific properties of our side lengths, and then the specific properties of our angles. I kind of spazzed out there. Sorry about that. So the properties of side lengths. Let's take a look at specific side length relationships. So as I've already stated, I basically already stated the basics of the general relationships among the correlation of parallelogram side lengths. But let's take a look at it in a different perspective. Let's take a look at it in terms of transversals, kind of opening up the topic. So each pair of opposite sides on parallelograms are parallel, which creates a transversal in order to develop theorems about angle relationships. So we know that opposite sides are going to be parallel to each other, meaning they have the same exact slope, and they're also going to be congruent, so they have the same exact length as well. But something that we know that's going to be created. So if we're taking a look at our top and bottom of a parallelogram, they're going to develop a transversal, because we know one side, when it intersects 2 parallel sides, that's the definition of a transversal. And with those transversal relationships, we can actually create theories about our interior angles of the parallelograms themselves and create those relationships amongst angles. So each pair of parallel sides are congruent, which helps in the development of the perimeter theory itself, in which we multiply each distinguished side by 2 and add them together. So this is our parallelogram here. And if you take a look here, these 2 sides are going to be parallel. So BC and AD are parallel. I'm going to write that down here. So sides BC and AD are going to be parallel, as shown. Now, one thing I want to do is I want to extend BC past this side AB. So I'm going to extend that right here as a line going in an infinite direction this way, like a ray. Let's say that. And then I'm going to do the same thing with AD. The same thing with AD. Like that. And when we extend it outwards, it's going to be just like an array. And something that you're going to notice here, if I just block this off here, if I just draw this out here, saying that this is the line right here, we just created 2 parallel lines in a transversal. This is going to be our transversal right here. Transversal. And when this transversal splits these 2 parallel lines as shown, you're going to have relationships amongst these given interior angles as shown, and also these exterior angles, which we'll get into in our later video tomorrow. Sorry, not tomorrow, next video. That's all it is, our next video, tomorrow. So in our tomorrow next video. let's just keep it like that tomorrow, because you guys are probably going to be watching these consistently each day. Hopefully you'll be watching this one a day. So probably your next lesson, you'll be seeing this. So these relationships created. Now let's look at the properties of angles. So angle relationships. This is very interesting, a bit way more complex when it comes to the angles, but these side lengths influence these angle relationships. So we have some sort of measure and consistency to base our calculations off of. So each pair of opposite angles on a parallelogram are congruent angles, meaning they're the same in measurement, and they're signified by this symbol. And what does that mean? It's basically the symbol, this congruency symbol right here. That's the congruency symbol. It's an equal sign with a little wave on the top. Let me just redraw that a little bit. I'll make it a little bit bigger. It's going to be an equal sign with a little squiggle on the top. Consecutive angles of a parallelogram are always going to be supplementary, and opposite angles created by the diagonals are always congruent. So there's this giant figure of a parallelogram with all these markings, but don't be worried. I'm going to break it down entirely, and it's much more simple. It's simpler than you think it is. These relationships are very important. So if we take a look at opposite angles, these are angles that have opposite vertex, directly opposite. So if we take a look at angle M and O, they're going to be opposite angles right here. And as you can see, opposite angles are always going to be equal in length, just as opposite sides are going to be equal in measure. So that's what influences that. So M and O are going to be congruent, and then I'm going to double circle P and N to show that they're congruent, to show those double angle marks. So N and P. So those guys are going to be the same exact measurement. And also another cool relationship is that consecutive angles, meaning angles that have lines that connect each other that go directly clockwise. So if we're counting clockwise, it's going to go from up, right, left, down. So it's directly up or directly to the right, not opposite. So as you can see here, M and P, they're going to be supplementary, meaning these guys are going to add to 180 degrees. Likewise with P and O, they're going to add up to 180 degrees. Same thing with O and N, 180 degrees. And finally with M and N, 180 degrees. That's another cool relationship. And we can prove that by utilizing our transversals. So let me clear up some space here so I can show you exactly what I mean by that. So let's clear all these things. So I'm going to extend these sides out like I did with my last problem with the side lengths here. I'm going to extend out OP a little bit, like that. Need a line or array, sorry. Okay, so we have our other array here, and then we're just going to extend it this way so that we can focus up on that, like that. So we have this transversal right here. So let me just label it transversal. So with this transversal created, we know that we're going to have these interior angles. The thing is, we know that these two are going to be interior angles of these two transversals intersecting this transversal intersecting these two parallel lines. What is something that we know about two interior angles? We know that two interior angles are always going to be supplementary. So we know same side interior angles are going to add up to 180 degrees. And that's the exact reason why all of these angle measures, consecutive angle measures, add up to 180 degrees, because of the same side interior angles theorem. All right, let's move on. Now I'm going to do a little bit of a parallelogram classification tree, just as a little break from that topic that I gave you originally, just so that you guys can start thinking about it. And also, this is extremely important because I've developed this chart just to show you the different breakdown of parallelograms and what are the different classifications they go amongst also. So first we have here our parallelograms, our father of quadrilaterals, I'd say. So that's our parallelograms right here. This is the basic structure. So this is going to be your parallel sides. Consecutive, it's going to have your consecutive angles. And then equal opposite sides. Equal opposites, I'm going to say equal opposites for both angles and sides. So I'm just going to leave it as equal opposites. So then the next classification, so the next two general types of parallelograms are going to be rectangles and then rhombuses. So I'm going to say rhombus or rhombi. Let's say that. Rhombi. That's our rhombi right here. Sorry. No two eyes, just one eye. So we have rhombi here. This is going to have property of equal sides. And this one's going to have property of, it's going to have equal sides and equal angles here. This is also going to have 4 equal angles here. And this guy's going to have equal angles. And then, of course, this is your square right here. That's a type of rectangle. But most people actually just stop here. Whoa, there's a giant gap between my T and my A. Don't know how that happened. So we see here that most people just stop here. Well, let's ignore the empty box that I have there. I'll fill that in last. But most people just stop here saying that, oh, the next type of rectangle is square. That's it. Square is only a type of rectangle in a parallelogram. No, your square is also a type of rhombus. People didn't realize that before. Because it has equal sides and equal angles. That's the same thing that a square has, except for the fact that it has it's 90-degree angles, but it also has those different properties. So technically, rhombi is a square. So rhombi does not have 4 equal angles, but it has 4 equal sides. But a square has 4 equal sides as well. Just it has an extra, an added qualification in which it has 4 equal angles. And then, of course, here our remaining quadrilateral is your trapezoid. And our trapezoid is its own section, not a parallelogram. And there's many different types of trapezoids, which I'll also get into. Not a parallelogram. We've already gone over the basics of parallelograms and the basic types, so I've already covered that, but I'll do some extended problems as well, so don't worry. Whoa, I spelled parallelogram wrong. All right, there we go. Let's move on now. And this is just going to be a transversal of a parallelogram, and we're also going to make some proof with it. So we can prove that consecutive angles of a parallelogram are supplementary by developing the informal proof through the evaluation of transversals. So we take a look at this transversal here. Same thing, if we just extend this line DC outwards. I'm going to change my pen to red here so that we can actually take a look at that in a different perspective, not so that my yellow isn't overlapping on the white. So let's take a look here. So if we extend out DC right here and make our own line right here along line DC, and then another line here along AB as shown, we know that this is our transversal. And basically what happens, it's not just these two angles that are going to be your supplementary angles that add to 180, but we can also take a look here and see that this side CB also represents another pair of same side interior angles with another transversal. So this is also going to be a transversal right here. And if we extended those lines out, that would also be 2 transversals intersecting 2 parallel lines. And therefore, these guys would also be your same side interior angle. So that's 4, let's say 2 pairs, sorry. So 2 pairs of same side interior angles. All right, to our last slide. Let's take that proof and make some formal proof and make a T-chart as I've shown here with our 2-column chart with our statements and proofs. So we know that we're just going to take that same example with those lines here. And what we're trying to prove is that all consecutive angles are supplementary. Okay, so let's take our first statement here. It's just a one statement, one proof. So we know that because I'm going to say here that consecutive angles are supplementary. Just that basic statement here. And how are we going to prove that? Well, we can prove that merely by saying our same side interior angles theorem. So same side interior angles theorem. SSA, so same side interior. Angles theorem proves that, and this is all in our formal proof. And don't worry, we'll get into that later in more depth in our probably a third parallelograms video. All right, everyone. So thank you for watching. This has been the eCoreAcademy e-learning platform. Please make sure to like and subscribe down below. And also don't forget to utilize that comment section down below to give us any feedback. We really appreciate it. And click that post notification button so you don't miss out on any of our newest course uploads. Also, check out our website at www.ecoreacademy.org. Just making an account for free there will give you full unlocked access to quizzes, worksheets, and note sheets that go along with each and every single one of our videos. Organized into their own course studies. Also, you can email us at eCoreAcademy@gmail.com if you have any questions, and check out our socials at Facebook, Twitter, and Instagram. Full link is down below. All the links shown on this page are accessed down in that description box, so please check that out at Facebook, Twitter, and Instagram. See what kind of interesting content we have there, and use those mediums to share all of our videos. Once again, everyone, I hope you guys enjoyed. This has been AJ. I had a blast making this video, and I'll see you guys in the next one. Peace.